So the first step here is to start mentor graphic Pyxis, and what we do, we launch something called the project navigator, and we do that from the terminal. So we're gonna launch the project navigator. So if you look at the navigator here, in the left side of the project is a project tree. So I'm going to show the project tree. So let me get there. And all the projects are basically concentrated from here. So here you can actually launch, interconnect, and all sorts of different tools that you like to use in a circuit. So again, so the left side here is the project tree. And the right side, we have the project files. And there are different folders. For instance, we create today the webinar July 2013 folder where we have all our projects. We're going to have the Mach-Zehnder modulator there. And the important one is the folder here, which is the generic Silicon Photonics PDK. So we are using a generic PDK to demonstrate the design flow without exposing a particular foundry PDK, which we require NDA in place here. So this folder contains a collection of design rules and files and process files, configuration files, files that are included with the Photonics package from Mentor Graphics. Now it also has a cell library with photonic elements. For example, you have the grading coupler, the ring modulator, phase shifter, Y branches. So these are modules that are included with the software, with the library. And obviously, if you are developing new elements, this library will grow to incorporate these elements, and this is part of PDK development. But let's start by creating an actual cell. Go there. So this is my slide, so I know where I am. And so we start by creating an actual cell here. So since we're designing a Mach-Zehnder modulator, we just start creating a cell called MyMZI. And we like to follow a schematic driven layout. So we start by creating a schematic first, which is straightforward. So in schematic editor, you can use different elements as building blocks of your circuit. So if you click refresh here, the symbol selector will be populated with elements available. So in the left side, you have the symbols for the elements of generic PDK that we show in the project navigator. So our Mach-Zehnder modulator will be placed between an input and an output grading coupler, as we saw before. So we start our circuit by placing them first. So we got our grading couplers there. Now, the naming conventions here for this particular element is, for example, GC is grading coupler, T means it's a T polarized, 1550 is the frequency of operation or the wavelength of operation. So next step then is to add the two Y branches. So we're basically starting our Mach-Zehnder modulator. Now, obviously, the modulation effect will be done by placing a PN junction to either arm of the modulator, and this is accomplished by this PN phase shifter here. So this is a basic PN junction on top of a waveguide. So in this case, the junction sits in the middle of the waveguide. So we place another one so both arms can be modulated. Now, if you zoom in here, you can see the Y branch name for the PN phase shifter. Let me go there. Now for the PN phase shifter, we have a list of parameters you can set for this element. For example, you can set the waveguide length and width. You can set the position of the junction relative to the middle of the waveguide. You can also set the load open ridge width. The element has two optical ports. More specifically, an optical input and an optical output, and two electrical connections to drive the PN junction, as you can see here. So you have two of those, right? You have a top arm and a bottom arm. Now to complete the circuit, we also need bond pads, so we need to get the electrical signal in, and so we can probe the circuit, we can simulate it. So for this, we're gonna add both. We do this for both of the phase shifters. Okay, so basically doing an electrical part. So now what's left to do is to connect the elements. So this means we have to create the nets. In the schematic editor, you can just basically, if you're using Pyxis, you can hit W and start drawing the wires. So this is really straightforward. So we connect all the optical elements here, and we will look later how this can actually turn into waveguides. And now we're going to connect electrodes as well, so we can get electrical signals in. And then after we do that, finally we have to connect the output to our grading coupler. So I'm going to do that last. Okay, so here we are. Now light will basically come into the grading coupler. The Y branch splits the light into two. Either one can be modulated. They are connected to electrical pads. Light is then combined back and goes to the output coupler. So it's everything here the way, in theory, it's supposed to be. So two waveguides and the electrical part, and this is the light going back to our output. Now we need to label our input and output ports. So this is really important because when you go to interconnect, you like to see those you have to know, what those ports mean. So you're going to see that into interconnect. For example, we have a top anode, top cathode, bottom anode, bottom cathode, and all of these ports will be also visible in interconnect later on. And we have to do this for both ports. Now we also define what kind of ports they are. Oh, by the way, we have to do first the optical ones as well. So we did all the optical inputs, and there is one optical input and one optical output. Now we also have to define what kinds of ports they are, if they are input ports, output ports, or bidirectional ports. So first we set the input ports, optical and electrical. Our compact model will find out by looking at the ports and by the position what kind of ports they are when it comes to interconnect modeling, for example. And we have the output for the grading coupler. Now I mentioned before there's a major difference between optics and electronics, and that's the wires or the waveguides. So what's missing here is basically waveguides that connect the different optical elements. So what we're going to do now, we're going to introduce waveguides into our circuit. So every time you place a waveguide between in a net or in a wire, it automatically splits the net into two and connects them to the waveguide model. So now when you look at the library, actually when you look at the netlist later on, you're going to see that waveguides are actually components, and they take properties such as width and height and length, for example. So we do this for every optical connection. When this is all done, we can basically save the circuit. And Pyxis is also going to check for errors, and there are no errors in this case. Now let's look at the SPICE Netlist export. So let's assume you like to simulate the circuit. We won't do that right now, but at least we can show you how we export netlists. At the end, we're going to then simulate. So that's the circuit we have. And what we do, we have to enter something called simulation mode. And that's simulation mode. So what happened now, we open the hierarchy navigator, and in this case we want to change the models from schematic to SPICE. So all our models should be represented by SPICE model. So that's something you need to do in order to create the netlist properly. So now everything is SPICE, which is very close to a traditional Berkeley SPICE file format. So now we can actually create a netlist. So now this is the netlist that we create. So here we have all the elements and how they're connected and their key properties. Like for the waveguides, for example, we have set the default length of 100 microns of all of them, and you can see them right now, all 100 microns. And so the key here is that as you change the waveguides and the location of the elements, you may have to refresh the waveguide length in order to accommodate for that. And in that case, you can regenerate your netlist. And what you can see here is the phase shifts as well. And it's initially set as a 500 micron length. Now we can go back. Now we change the properties of the phase shifters, and for our example here, we're going to be setting them to 1 millimeter. So going to be kind of traveling wave type of modulator. So we set them to 1 millimeter. So what we can do now, we can go to the simulation mode and export the netlist again. And in this case, what we like to see is to have 1 millimeter as a waveguide length for both phase shifters, and that's what we have. So you can see right now, as you change properties, you can always refresh and regenerate the netlist. Now, Interconnect needs another file. Typically, you like to think in Interconnect only of simulation tool, and you don't have to worry about the position of the elements. But because we like to debug the circuits, it's nice to know where the elements are. And Interconnect, when you use Pyxis, they can actually export for you a position file, and this file then tells Interconnect where to place the elements. So you end up temporarily with two schematics, one in Pyxis and one in Interconnect, which is important for debugging. And when you do that, then you can export your circuit and exit. So let's look at creating the layout. So we can see now the Mach-Zehnder files that we were created by schematic editor. You can see there is a netlist there, and there is also the position files. So that's the netlist. That's the last one we created. We can see the position files, so it's quite cryptic, but this is basically what Interconnect uses to find out how to place an element, whether it's rotated, whether it's flipped or not. And we have the schematic file. So let's start the physical layout. So we can basically start the folder and create a new layout. And we can use all default properties in this case. Now this will automatically open the schematic in read-only, so you can always have the schematic as your reference here. And what you do, you can select all the elements, the optical elements, for example, or all the elements you want, and you can place them into the layout. And to do that, you use a tool called Auto Inst, or I guess it's Auto Instance. So you select that. So these are the elements we like to place in our layout. Now, when they're placed in the layout, they're somehow arranged as they were in the schematic editor. So here we can zoom in and see the grading coupler, for example. So we're going to go there. So you can place them properly, and as you're moving them around and you put waveguides later, this is going to have an effect on your simulation. This is our Y branch. Notice that we're not connected to waveguides yet. We are just using nets information that came from the schematic. Later on, we're going to add the waveguides. We also have the two phase shifters and the electrical pad. Now, a simple waveguide branch is not at all complicated. It can be defined in one layer. This is not the case of the phase shifter. So if you look at the phase shifter, yeah, so this is the Y branch, and you see it's pretty much silicon. But you look at the phase shift, there's quite complicated in terms of cross section. So for example, the phase shifter require multiple layers. So we have predefined layers. We have here the silicon on red. We have different layers with different edge depth, as well as doping layers, metal layers, a variety of different layers. And this is all coming from the PDK as a set of predefined layers for your process. They're all identified, obviously, with different colors. And there's many properties here related also to the PN junction. Now there is a tool called cross section, and it's really useful because you can actually see, you can cut the cross section of the waveguide and you can see all these layers. And this is very useful actually. So what we're going to do here, we're going to use the cross section, and we're just going to cut a slice of our waveguide. So here we go. So what we have here is basically the waveguide. It's a ridge waveguide with the actual waveguide in the middle. And you can see the p-doped, this is basically the p-doped region. Then we have the p++ doped region, the n-dope, the NPP dope region. So this is all defined here. You can easily see by using this cross-section tool. There's also the via, the contact via. It goes up to the metal layer, and you have the oxide, buried oxide layers. It's a really good tool if you are designing a new device. You want to verify the cross-section. Let me close that. Okay, let's go a different way now. Let's change things in the waveguide and see how that's going to affect our schematic. So you're going to start by rearranging the layout. So the first step here, and is stay on here. Just going to have to align all these different pads. So I have to do this a few times. And obviously there are a few tools to do that. So you can align them and place them properly in your layout. And later on, this will be important because when we actually set the wires, it's good that they're properly aligned. So it's going to be easier to set to change the width of the metal part and also the via. So we're basically aligning them. Yeah, so when we do that, then we're going to go to the Y branch, and what I like to do here is to create this unbalanced modulator. So we're going to move around the Y branch later on. So then we end up with a different waveguide length for the bottom and the bottom arm, so they'll be different. So using 150 microns here. And I guess we are done here. So let's arrange the Y branch here. So this one is basically the distance between the Y branch and the phase shifters are pretty much the same. And now what we like to do is to set the waveguide. And you're going to use a tool called iRoute. So with iRoute, we're just going to go and set all the waveguides. And you see that right now by default we're setting all these waveguides with sharp corners. So we don't want to have that when you fabricate, but this is the way you're gonna get started here. So you're gonna set all the waveguides, and this is the optical part first, which for the modeling part will be enough to get started. So this is what I was actually moving around the Y branch, so we get now different distances for the two arms of the modulator, so then we can have unbalanced modulator. So connecting to our combiner here, and now we're gonna go all the way back to the output grading coupler. Now we have the waveguides, but obviously we need to convert these sharp corners to bands, so that's a problem. So we have a huge amount of losses here, even assuming this will even work. So what you can do now, you can select all the waveguides, and then using some of the tools we have for the Photonics package here, we can call the make PWG function. And this function allows you to change the band radius. You can also change the band type. You can use the radial. You can use a Bezier curve, and so on. So then when you do that, just press OK, and then Pyxis takes care of that, of changing all the sharp corners to actually waveguide bands. So we do that, and now we have all the waveguide bands. So if you zoom in, you can see now part of the hard work was done for us here by actually letting Pyxis do that. Now that we have these waveguides, we actually can use a waveguide parameter file. And that waveguide parameter file contains now the length of those waveguides after you place them in the layout and after you move all these elements around. And that can be then mapped back to our schematic. So now our schematic, we have the right properties as far as the distance between the different elements. So let's go back then to the schematic. So the file then is exported. So you're going to go there, we're exporting that. So from the project navigator, we can then reopen the schematic. And then what we're going to do, we're going to select specifically the waveguides in the circuit. So the component type will be the waveguide, which is called PWG. and we're gonna do that selecting those elements, and then we can update the waveguides from a file. So we provide the file we created before, and now what's gonna happen is the length of each segment will be updated. So you can see here 84 microns, so this was updated from the file. You can see here this waveguide has about 75 microns and 71, so it's slightly different. Here you have about 78, and this is 33. So you see it's really unbalanced now. You can see that there's quite a difference between the length of those two waveguides. And now we can then create a netlist using the process we did before. But this time we do have the updated values for all the waveguides. So you can see all this, the 33 micron, the 78 micron. So all these different files define your netlist. So we can actually simulate this here. But before we go there, let's finish the circuit, because we didn't finish. We still have to do the metal part. And then we're going to use iRoute again. And then as we route, we actually can change the layers and the width. So as you change layers, it automatically adds the proper via, and we'll repeat the steps for the pads for both arms of the modulator. And this is where these tools are, they basically dominate. This is electronics, so it's really straightforward to do that. You don't have to think about the sharp corners and all the details that we have to be worried about that when you are doing the optical part. And the alignment that we did before is really helping out, so it makes it really easy to connect these things. Okay, so ideally this circuit could be fabricated. So we could actually, put that in our wafer, and after a design rule checking, you can go for fabrication. So we have our grading couplers, we have our waveguides, we have the proper bands. We have the mechanical part, so we can actually drive this device. We have our Y branch there. So all the steps are actually done. So now let's do the verification part. So let's import a netlist using INTERCONNECT. And these are all the files that were created before, right? You can see the parameters for the waveguides, the positions, and the netlist. And that's all we need to go actually to INTERCONNECT for the verification part. Now the project navigator already incorporates numerical interconnect, so we can actually start directly from the navigator. To make sure that we use the same working folder as the files that we like to load, for example, files that were created through parameter extraction, we actually create an empty project and we save the same place where we have our files. So it's going to be my MZI ICP, which is an INTERCONNECT project file. And then we do import SPICE netlist. So that's very important here. So we are loading that file we created before. And in INTERCONNECT, that's basically translates to a script file. So it's the numerical script. And then this is how we actually translate the files. So when you run the script, what you get now is a compound element, which is INTERCONNECT is a subcircuit, which contains all the input and output parts that we actually created before by using the schematic editor in Pyxis. So if you look inside, we have actually the circuit, which is equivalent to the same one, or have to be the same one that we had in Pyxis. So we have our Y branches, we have our grading elements, we have our modulators. These are all now compact modules that they exist in INTERCONNECT, which means you can simulate them. Now in Pyxis, they were actually symbols and elements that you can actually see their geometry or their layout. In INTERCONNECT, they are related to the modeling part, not to their geometry necessarily. And now when you change those properties, you can actually be looking at parameters that were previously extracted using our other tools. So this actually brings everything together. So, but now let's actually see the frequency response of this device. So let's perform a frequency domain analysis. Well, for frequency domain analysis, INTERCONNECT is quite straightforward because you can use the optical network analyzer. So we're gonna place the network analyzer here, and we're gonna send light to our input part, and let's measure the output part. Now this optoelectronic device, we have to actually drive it. So we're going to add DC sources here for our cathode for both arms of our modulator. You have to provide that to interconnect. So you have to provide some voltage value. And now when you provide the voltage value, you basically change in the correct effective index for that particular waveguide based on modulation. So now it's all connected here, and we use just 0 volts, and the idea is just to run the simulation, and what we like to do is just to find the frequency of operation, in this case for our Mach-Zehnder. So you're going to increase the frequency range for the analysis. We will not increase the number of points. The 1000 points should be enough. So increase the frequency range, and then we basically just run the simulation. In this case, the frequency response will be based on the center frequency of reference. So it's going to be, when you see the plots, they're going to be centered at 0. So you look at the results view, and we choose gain here because we really want to find the frequency of operation. And then what you see here is a typical response you like to have from unbalanced Mach-Zehnder modulator. So you see this different peaks. INTERCONNECT does have a peak detector. We didn't use the peak detector here. We should have. So we actually can find exactly where that peak is located. But it was as easy as just zooming in and actually looking where it is. So these are the different peaks, and then you're just going to try to find where the center is. Now, because we set the value to be centered at 0, we're going to actually change the simulation to use the absolute frequency value. So it won't be relative to the center frequency. So we change that, and then we just run the simulation again. Okay, so this is the response, and now what you would like just to find what's the frequency of operation that we're going to set the device. So it's going to be about 193.065. So that should be enough. So that's where we're going to actually set our source. And this is again, it's just to demonstrate the process. I'm not getting to all the details about the modeling requirements for Mach-Zehnder modulators. So let's then do a time domain analysis. So two ways to do that. Usually I save this as a separate file, and then I just set the drivers and the sources in my eye diagram analyzer. For example, here what we did, we just used the same file. It's just easier, and it's easier to demonstrate. So I can use the same project. Obviously, when you run the project, you have more elements. It takes a little bit more time to run. But in this case, it's still this is all real time, so it's going to be pretty much instantaneous. So I'm going to use an eye diagram. I think it's a good way to see it, the classic time domain measurement. We are starting here actually by the receiver side, so we're going to get the eye diagram. We're also going to choose a photo detector here. We set our source, and in here case we're gonna set to the input, and then here is gonna set that frequency value we measured before. So we set to 0.65. Okay, now we're gonna choose a photodiode. And we will set this. I think the frequency response is pretty much flat here in this example, and I think the noise also has no impact on this particular design. So we also set the frequency operation of the device to 93.065. Then we add a Bessel filter here, a low pass filter, order 4, so it shapes our signal properly and also removes any unwanted noise from our photo detector in this particular example. We really want to do a back-to-back response to the device. So that's our signal that's going to go to the input of our eye diagram, and finally we set the reference signal, which is going to come from our non-return to zero pulse generator. So use a PRBS, so you're going to set a sequence of bits, and we're going to use a non-return to zero pulse generator. This is not going to be a push-pull type of configuration, so we're going to only drive one of the arms of the modulator. And we're using the full values for the amplitude and bias, so for the voltage. You can obviously characterize the device response and then get all these values exactly as they are supposed to be. And for the other arm, we're just going to set a DC voltage. So what we have here is basically our basic, transmitter setup, which is similar to the slide I showed before, which we're trying to do. And inside of this device, we have all the things we need. Now, this is going to be a 2.5 gigabits per second, so it's really, we're going to use default properties for that. I tend to think in digital signals better, so I will set to use a default samples per bit, which defines your sampling rate. But I'm going to change the sequence length to 64 bits here, so we have enough bits for an eye diagram. And we basically then run our simulation. So you can see this is the percentage of the simulation that's completed, and then we have our results available. Then we select the eye diagram. And this is our eye diagram. So in summary, what we demonstrated today was how to export a modulator circuit from Pyxis all the way to INTERCONNECT. We show you the schematic driven layout, the layout driven schematic, the circuit simulation and verification as well. So INTERCONNECT actually used here mapped compact model parameters, so it seems to be really straightforward, or I believe so. When I was just using Pyxis and exporting to INTERCONNECT, I was creating the circuit, I was running the simulation, everything was working. But the truth is the models that you saw in that circuit, they were previously characterized. So that part of the work was already done for me. So I was only really concerning how to put my Lego pieces together and run my simulation, which is what the future holds for all of us if things move properly, right? So we be able to actually start from a schematic in an optical circuit the same way we do for electronic circuits. So we use mode solutions for the waveguide characterization. For the passive elements, we use FTD solutions, and for the active devices, we combine a device with mode solutions.